Hi, everyone. Let's work through question 6 from the January 2022 CSEC Physics Paper 2. So part A of question 6 is asking us what is meant by the term the nucleus of an atom, right? And so we can say that the nucleus of an atom is the extremely dense part of an atom, right? It's in the center of the atom, which contains positively charged particles. Those are our protons, as well as the neutrons, which don't have any charge, right? So I think as long as we hit on the point that it's extremely dense, it's a part of the atom, it contains the protons and the neutrons, I think that we should be good for these 3 marks here. Okay? So moving down to part B reads, radon-222 is a radioactive nuclide which decays spontaneously with the emission of an alpha particle to form polonium, right? The nuclear equation representing the decay of a radon nucleus is given below, right? So we see here we have our radon nuclide that gets decayed to form AZPO, so that's polonium. And of course, in the process, an alpha particle is emitted, right? So this is our alpha particle here, which is equivalent to a helium nucleus, right? So that's why we see our 4,2 alpha. Okay. So this is the nuclear equation which represents that decay, right? So part I is saying, state what is meant by this term spontaneously, right? So remember up here, it says that the nuclide, the radon-222 nuclide decays spontaneously. So what does spontaneous mean? I guess in this context, specifically. And what it means is that the decay can happen at any point in time and it cannot be predicted, right? So it will just happen at any point in time and nothing can really affect that, nothing can affect when that will happen. It's just something that happens spontaneously. Okay, no external forces can predict or can affect that process. So that's what we mean by it spontaneously happens, and that's for 1 mark. If we say all of that, we're good to go. It's just any point in time and we can't predict it because we can't control it, okay? Okay, so moving down to part 2. The question is asking us to determine the values of A and Z in the nuclear equation above. So here is our A and here is our Z. So remember now, we said that whenever there's an alpha decay taking place, which we know based on what we see here, and they told us that an alpha particle is being emitted, we know that the mass number is going to decrease by 4 and the atomic number is going to decrease by 2. So whatever is over here is going to have a 2 less in the atomic number portion. So we do 86 minus 2 gives us 84. And then from the mass number standpoint, now we're going to subtract 4 from this mass number over here. And so we end up with 218. So 218 is our new mass number and 84 is our new atomic number. So effectively what we end up with is that we end up with, let me just write that here for completeness, we'll end up with a 218, 84, right? PO, polonium nuclide. Okay, so that's what we'll end up with. That's our final product because we subtract 4 from this and then subtract 2 from this to end up with this nuclide. Okay, so all of this calculation, this part I think is all that we needed to do to get our 2 marks, and we are rolling, we're moving along, right? So let's move down now. Let's go down to see what else is being asked of us. Okay, so we're at part 3 now, part 3 of that question. And it's asking us to use Einstein's mass energy equation to calculate the energy released during this reaction, right? So we know that these kind of nuclear emissions release energy as well as a part of this, a part of this formation of this new element, there's energy that's released as well. So we can write from 2 then, well, first of all, or relativity, right? Our equation to relate the mass and the energy is delta E is equal to delta MC squared, right? And delta E is just the energy change that happens, and that's correlated to this change in mass, we call this our mass defect, right? So this is the equation that we have to zero in on immediately when we're asked to find energy released, right? So we zero in on this equation right away. We pull for this equation, we write it down, right? So then now we can say, okay, let's go back up to part 2. So from part 2, this was the equation that they gave us, right? We were able to find out what A and Z was, right? So we know that these values now. And so we can come down here and rewrite that equation. So it's 22286. That's that radon there, right? So that's that radon that's going to now 21884 polonium. It's giving off an alpha particle because that's what gets emitted from over here, as well as energy, right? And that energy comes from that delta M, which is what we refer to as that mass defect. And that's what we're going to be needing to find to be able to then calculate the energy using this relation up here, okay? So in order to do that delta M, that mass defect calculation, on this paper, right down here, they told us what the masses of the nuclide actually are. So they saved us a bit of work. So they told us what the mass of the nuclide are. So in this case, they told us what the mass of the radon nuclide is. So that's this. They told us what the mass of the AZ, so these were unknown at the time, but they knew what it was, right? So we came up with what the actual identity or the value of A was and Z was, but it's the same species that has a mass of 361. And so we just kind of write that one down here, right? So that one is for this. And then now they told us what it is for the alpha particle as well, and that's this number, right? So we got all these numbers from down here. Ordinarily, we would have to calculate this by ourselves, the mass by ourselves, by multiplying the mass number by the mass of one atomic unit, and they would give us that value. But they saved us some time here by giving us this table, so that was great of them to do. So we just plug these numbers in up here, right? So this is the mass for the radon nuclide. This is the mass for the polonium nuclide, and this is the mass for the alpha particle that gets emitted. And of course, our delta M is what we're trying to find that's associated with this energy that was also emitted, okay? So in order to get this delta M, we want to isolate our delta M, and so we bring the sum of these two masses to this side. And so when we do that, now we end up with 368.54918 times 10 to negative 27, and we subtract this from all of this over here. And what we end up with is a mass of 9.63 times 10 to the negative 30 kilograms, right? So once we get our mass or our delta M or mass defect, then we can plug that now into our equation for delta E, which is delta E is equal to delta MC squared, right? So we're literally just plugging in this number now here for delta M. We know that the C is the speed of light, and that's squared, the speed of light squared. So we come down here and we just plug in those. We put all of this into our calculator and we come out with a delta E of 8.667 times 10 to the negative 13 joules. And that's our answer, right? So that's the energy that was released during that reaction. So all we have to do is just find our mass defect. We know our Einstein equation, so all we need now is our mass defect. And that we can calculate from this nuclear equation here. And so we have the masses, so we can find our mass defect. Want to find our mass defect, we plug that into the Einstein equation to then come out with what our energy released was, okay? So that's how we will approach this type of question. Moving along now, let's see what part C is asking us. So part C is saying that there's a fresh sample of radon-222 gas, which has a half-life of 3.8 days, right? So again, we said half-life is how long it takes for whatever I started with to be halved, right? So it takes me 3.8 days to halve my sample. The mass of the sample, however much sample I have, it's going to take 3.8 days to end up with half of that amount. So here for part I, they're asking us to define the term half-life. What is a half-life? So the half-life of an isotope or of a species in general is the time taken for the mass, right, of that species or the activity of that given sample to decay to half of its initial value, right? So if I start with 10, how long does it take me to get to 5, right? That's half of 10. So that would, the time that it takes to do that is what we would refer to as the half-life, right? So this is our definition for half-life. We hit on all the points that it's half of the initial mass and the time that it takes to go there. We get our 2 marks and we're good to go, okay? So moving down to part 2, part 2 is asking us to calculate the mass of radon gas remaining after 15.2 days, right? Giving your answer to 2 sig figs, right? So to do this now, they're giving us an endpoint in time, right? They're giving us an endpoint in time, and we know what the T half is. The half-life is from up here. We know the half-life is 3.8 days. We know that we're starting out with 240 grams because that's what we had initially, right? So we know we initially have 240 grams. The half-life is 3.8 days. And they're asking us after 15.2 days, how much radon 222 gas will we have, right? And so again, what we can do first of all here is find out how many half-lives are there in 15.2 days, right? And so to do that, we say, okay, 15.2 days divided by the half-life, which is 3.8, gives us 4. So that means that we have 4 half-lives. We're going to go through 4 half-lives by the time we get to this 15.2 days, right? So that being said, if I'm starting out with 240 grams, right? As I go through my first half-life, that will be halved and I'll end up with 120 grams. I go through my second half-life, this is going to be halved and I'll end up with 60 grams. I go through my third half-life, this is going to be halved and I'll end up with 30 grams. I go through my fourth and final half-life to get to the 15.2 days. This will be halved and I'll end up with 15 grams. So after 15.2 days, which is 4 half-lives, I'll end up with 15 grams of radon-222 gas. So this is our answer, right? And with that, we come to the end of this question. For 15 marks, we should be good. If you have any questions, if there's anything about this that was unclear to you, definitely drop a comment below. I'll be happy to address that. And while you're here, just give this video a like, make sure you're subscribed to the channel, and I will see you in the next video.